In this section, I'm going to introduce you to the difference between organic and inorganic compounds. This chapter is all about organic chemistry, so let's see what the difference is. I have here two examples that you might be familiar with: milk and salt, table salt. Which one do you think is organic and which one do you think is inorganic? Well, the definition of something that is organic is not whether it's raised naturally, has no genetic modification, or you don't use pesticides or whatnot. That's the conventional term for organic. In chemistry, organic has a more specific definition. A molecule is considered organic if it simply contains one criterion, and that is that it contains a carbon. So let's take a look at some of the ingredients in milk. Looking at the nutritional facts, we see that milk has sugars, and sugar is an organic compound. It also has vitamin D and protein, both considered organic compounds. But there are also inorganic components in milk, namely calcium phosphate. Calcium phosphate is considered an inorganic component in milk, whereas table salt here, what is table salt composed of? Table salt is basically NaCl, right? There is no carbon in that compound. So salt is our prime example of what an inorganic compound is. So that's the two differences. Let's talk a little bit more about organic compounds. We already said that it contains a carbon, right? But not all things that contain carbons are considered organic. Actually, there are a few exceptions. These exceptions are very small. Most notably is carbon dioxide, carbon monoxide. That is not considered an organic compound. And if you have polyatomic anions that contain carbons, those are not considered as organic compounds. Those are going to be part of an ionic compound, right? So for example, carbonate and cyanide. Those are your few exceptions. Other than that, whenever you see carbon in a molecule, that tells you that's going to be an organic compound. What are other atoms that are in an organic compound? You will oftentimes, most of the time, hydrogen. In fact, hydrogen is found almost all of the time. Besides from hydrogen, you may also have other atoms. For example, oxygen, nitrogen, sulfur, phosphorus, and lastly, halogens. Some examples here is sugar. Sugar is composed of 12 carbons, 22 hydrogens, and 11 oxygens. Now, when you write the molecule of an organic compound, you start with carbon first, then you write hydrogen, and whatever atoms comes after that, you want to alphabetize. Okay, so another example, vitamin D, you say CHO in that order, 27 carbons, 14 hydrogens, and 1 oxygen. Lastly, we see here glycine, which is an amino acid that makes up the protein. Has carbon, hydrogen, nitrogen, and oxygen. You see that nitrogen is written before the oxygen because of alphabetical order. So glycine is written as C2H5NO2. So you may have noticed that the organic compounds are covalent molecules. They contain nonmetals, and because they contain nonmetals, electrons are being shared, therefore all you see are covalent bonds. Speaking of covalent bonds, let's review the Lewis structure for molecules that contain that carbon, since all organic compounds contain a carbon, correct? So let's go back to the fundamentals. How many valence electrons do carbons have? Carbon is in column number 4, so it has 4 valence electrons. Right? And so that's how we would draw the Lewis representation of carbon. Now, if you have only 4 electrons, how many more electrons do you need to become a happy atom? You need to obtain octet of electrons, right? So you need 8 electrons. So how many more interactions, how many more electrons does it need? It needs 4 more electrons. Because it needs 4 more electrons, it's going to covalently bond 4 more times. So for example, our most simple case is when you have Ch4 methane. This is the gas when you cook at home, right? So hydrogen is 1 electron coming in. So it can come in and share that. Another hydrogen can come in and share that, making another bond, and then another, and then another. Okay? This is the sharing of electrons between carbon and 4 other hydrogens. So remember that we represent this in every time a pair of electrons being shared, we represent with a single bond. Let's take a look at another example of an organic compound, C2H6. Okay, now we have twice the number of carbons. So carbon, turns out it binds with another carbon and has 6 hydrogens. So 1,
2, 3, 4, 5, 6.
This is another organic compound called ethane. Okay, so notice what is similar between these two compounds. How many bonds does carbon have? Carbon has 1, 2, 3, 4. Right? Every single time when you draw that carbon, it's going to have 4 bonds. No matter what, carbons will always have 4 bonds, even if it's going to double bond to something. So for example, formaldehyde. Remember the structure for formaldehyde from our previous lesson? Right? It is bonded to 3 atoms, but still it has 4 bonds, right? 1, 2, 3, 4. The double bond counts as twice. And the reason for that is, again, it needs to have an octet. In order to have an octet, you need to bond 4 times over. The second point I want to make here is the geometry of the carbon. If a carbon has 4 electron groups, what is the geometry of that central carbon? Right? It is tetrahedral. So remember, the tetrahedral is drawn with representation with 2 things on a flat surface, and 1 coming out at you and 1 going away from you. Whereas this one, remember, is only 3 electron groups, so this is trigonoplanar, so it already is in its 3D shape.